So far we've only been talking about velocity, and we've been, so velocity's units are, it's a position over time, but we could talk about like other things other than velocity. Like we could talk about how is temperature changing with respect to time, and that wouldn't be velocity because temperature isn't a measure of distance. Or we could talk about like how is voltage of something changing with respect to time. So we're going to look at other rates of change. So these other rates of change will give us a couple of quick things. So instead of using a position function, we're now just going to talk about a general function, delta f. So delta f will equal f of, and we're going to use x1 and x0 because you don't even necessarily need to be talking about like time necessarily. You could say how is temperature changing as a function of current, or you know, how is money changing with respect to maybe interest rate or something else that's not time. And these are rates of change that we can talk about. So we're just going to kind of generalize those initial two equations we worked with a little bit. So instead of using delta s, s of t1 minus s of t naught, it's going to be delta f is f of x1 minus f of x naught, and we're using x's instead of t's. So instead of getting the average time, we could say average velocity equation. Now we get an average rate of change. So the word rate of change, that kind of stands in place of velocity. This would now equal delta f over delta x. And this would equal whatever the f function is evaluated at x1 minus the f function evaluated at x naught, all that over x1 minus x naught. So this is a slightly more general form. Instead of talking about velocities, we're now talking about rates of change. Whoops, need an E on it. And it can be any function f now, and x can be anything. It doesn't have to be time. So then we say, well, the instantaneous rate of change we could say at x equals x naught, or x0. Sorry, x naught in physics, a lot of professors I have use the term naught for zero. So you'll hear me kind of, sometimes saying naught instead of zero. So it's N-O-U-G-H-T. So what's the instantaneous rate of change at x equals x0? Well, that would be the limit of the average rates of change over smaller and smaller intervals. So we look at the average rate of change, say start at x0, go out to a value, and as we let the value that it goes out to get closer and closer to x0, where we're looking at x0, then maybe like a millionth beyond it, and then an x0 and a billionth beyond it, the limit of those average rates of change will become the instantaneous rate of change. So the instantaneous rate of change at x equals x0 is the limit of the average rates of change as the interval gets smaller and smaller. Okay, so basically it's the same thing that we just did in like example 1, where we looked at dropping a stone, and we said, okay, let's look at all these different average velocities and look at 0.8 to slightly beyond 0.8, and all those average velocities start approaching the same number, and then the number they approach is the instantaneous velocity. We would do the same thing to estimate an instantaneous rate of change. It's just we can't really call it velocity anymore because f no longer has to be a position function, and we're not necessarily talking about t for time. We're talking about x that could be time, but also could be something else. So this is virtually the same thing we did in example 1. The equations are the same. It's just now saying it doesn't have to be position in time always, and if it's not position in time, then you can still talk about it as average. You wouldn't use the word velocity anymore. You would call rates of change and instantaneous rates of change instead of the word velocity.